Okay, welcome. It's time for Module 11 in week 12. This is Wednesday of week 12. We're looking at the shape of the graph. So what the derivative can tell us about the graph of a function, and in particular, we're interested in extreme values of the function. So this is something that we've looked at since the start of class. What is the relationship between a derivative and its function? In particular, what does it make the graph look like, of the function look like? So most important is the sign. So if the derivative is positive, the function is increasing, negative, decreasing. If the derivative is zero, it's flat. And then the second most important thing is, what is the magnitude? So big magnitude means steep, small magnitude means gradual slope. And if the derivative is a constant, is constant for a while, then the graph looks like a straight line. Okay, and so as I said, we're interested in kind of looking at extreme values. So here is some vocab for us. So we're interested in the distinction between minimum and maximum, and the distinction between global and local. And I think examples are the easiest way to show this. So if you look at x equals a, you see there's a nice hill there, and we have a global maximum at x equals a, right? Because f of a is greater than or equal to f of x for all x. So the greater than tells us it's a maximum, for all x tells us it's global. There's no global minimum since we have that asymptote at x equals 0. So there's no actual number where f of e is less than or equal to f of x for all x. So there's no global minimum. However, there is a local minimum at x equals b, because f of b is less than or equal to f of x. That makes it minimum for all x near b. That's what makes it local. So there's like a little valley shape there. So the first module question then is, what type of extremes do we have at x equals c and x equals d? So here is an example then. Let's say we're asked to sketch a graph that has a local minimum at x equals 3, a local maximum at x equals 8, but no global maximum or minimum. Okay. So here is, I've just opened up Paint. And so we've got a local minimum at x equals 3. So here we want some kind of valley kind of thing. So since it's going up at x equals 8, we want a maximum, so we better make it above there. So we should make it around here. Okay, so then we just got to join these two things up. Now there's no global max or min. So that means, oh, terrible. That means we have some kind of asymptote that looks like this. Sorry, I shouldn't use the mouse again. And then it hasn't got a global minimum, so it's going to sort of go down like that. So here we see the local min at 3, the local max at 8, but nowhere is there a biggest value. Okay. Okay, so if we look at the second derivative that we just learnt about, we know that if there's a positive second derivative, the graph is concave up, and if it's negative, it's concave down. So here we have some situations. So here, at this point here, the function is increasing. So the first derivative is positive. It's concave up. So the second derivative is positive. Here we've got going down. The first derivative is negative. but it's concave the other way, so the second derivative is negative. Here, again, we've got it increasing, so the first derivative is positive, but now the second derivative is negative, right? Because it's kind of shaped like this. It's concave down. Here, the first derivative is 0, because we're at the top of the hill, but the second derivative is negative. Here, the first derivative is negative, but the second derivative is positive, right? Because it's concave up. And here, the first derivative is 0, and the second derivative is positive. So this kind of shows you that you can have any combination of f prime and f double prime being negative or positive. So this is a thing that I went on about the function and its derivative, that just because one is positive doesn't make the other positive. Remember, the derivative being positive just means it's increasing. Okay, but this is going to be helpful, right? Because here we've got a nice little maximum here, and here we've got a nice, and in D we've got a nice little maximum there, right? The second derivative is negative, and the first derivative is 0. Here we've got a nice little minimum in F, where the first derivative is 0 and the second derivative is positive. Okay, so what we really want to be interested in is optimization problems. And this is a really classic calculus problem. I give you a function or I give you a situation and you're supposed to find the best value. So what is the maximum? What is the minimum? So our first guess based on the previous slides would be to look for the tops of hills or the bottoms of valleys. That is places where the function is flat, so the derivative is 0. That's kind of true, but we have a little bit of technical complications, which the next two examples will show you. So the first one here, we've got x cubed. The derivative of x cubed is 3x squared. At 0, the derivative is 0. But you can see that there's no extreme values at all. There's no global max, no global min, no local max, no local min. Another example is x to the 2/3. Its derivative is 2/3 x to the minus 1/3. And if you look at it, there's what's called a cusp. There's a global minimum at x equals 0, but nowhere is the derivative 0. So basically, these are the only kinds of things that can go wrong. So we've got to just take these into account. So here's the technicalities. A critical point for a function is a point where the derivative is 0. That's okay. That means you've got a nice top of the hill or bottom of the valley. It's infinite. That's when you get the cusp, or it fails to exist. Something we haven't talked about, but I need to mention now, is the idea of a continuous function. So a function is continuous on an interval if its graph on that interval is continuous in the usual sense, like the everyday sense of continuous. That means there's no gaps, no jumps, no asymptotes. And there are two important principles that functions obey. First one is that a continuous function on a finite closed interval has extremes. So remember, a finite closed interval, like you go from 1 to 3, or 2 to 7, whatever. So it's finite, it's got a length. It's closed. That means it includes the endpoints. So an open interval would be like if you use a bracket, closed if you use a square bracket. That's the convention. Okay. And then the second principle is that continuous functions have extremes only at the endpoints or critical points. So if we have a look here, the examples there, C is the maximum for the function, right? So in the first one, we've got a nice flat hill. In the second one, we've got the derivative doesn't exist there because we're at a corner. And in the third one, the maximum happens at the endpoint because the function is just increasing all the time. Okay, technicalities over, let's go back. So how do we find local extremes? First, you determine the domain of the function and identify its endpoints, if any. So sometimes you're given a question and it's got endpoints given into it, given explicitly the endpoints. Other times, there's an implied endpoint. For example, if you're talking about square root of x, right, you can only do that when x is greater than or equal to 0. So 0 is an endpoint, even though it might not be mentioned. Okay, so once you have the function and its domain, you find its derivative. Then you just set that equal to 0, and you find all the critical points that way. Next, you look for any points where in the domain where the derivative is undefined. Okay, then when you've got a critical point, you have to classify what it is. Is it a maximum, is it a minimum, or is it neither? Okay, so there's different ways you can go about doing that. If you can graph it, then you can just look at its graph and you can see whether it's a max or min. You can look at the first derivative and you can look at either side of the critical point. Okay, so if the function is increasing, i.e. if the derivative is positive before and negative after, that means you've got a maximum. If it's negative before and positive after, that means you've got a minimum. If it's positive before or positive after, like in the case of x cubed, you've got neither. And the other thing you can do is you can look at the second derivative, right? So if the first derivative is 0 and the second derivative is positive, that means you have a valley at c, so you must have a min. Whereas if it's flat and the second derivative is negative, you have a hill, so it must be a local maximum. Okay, either those ways will be good. So just let's have a look at some examples. Here's some local extremes. Let's have a look at cube root of x. So the domain of that is all numbers. Its derivative is, right, it's x to the third, so down comes the third and you subtract 1, so you get x to the minus 2/3. So the critical point is x equals 0, right? Not because the derivative is 0, but because it does not exist there, because you can't put 0 into the negative 2/3. That first derivative is always going to be positive, right? Because you've got the 2/3. The 2 in the numerator means that it's the cube root of x squared. So it's always going to be positive. So the derivative is always going to be increasing, except at the point x equals 0. So that critical point is neither a max nor a min. Okay, another example. X cubed plus 3 halves x squared minus 6x plus 5. Again, the domain is all numbers. We take the derivative, we get 3x squared plus 3x minus 6. We factor and pull out a 3. So we're left with x squared plus x minus 2. And we can factor that again as x minus 1 times x plus 2. Or we could use the quadratic formula, minus b plus or minus the square root of b squared minus 4ac on 2a. If we do that, we find that the roots of that are 1 and minus 2, so those are the critical points. Easiest thing here to do is to do the second derivative, which is 6x plus 3. So at x equals minus 2, the second derivative is negative. So x equals minus 2 is a maximum. At x equals 1, 6x plus 3 is 9, is positive. So x equals 1 is a minimum. Okay, so it goes up, down, up. Okay. Here's another one, 2x plus 1 divided by x minus 1. Domain is all numbers except x equals 1. So 1 can't be a critical point because it's not in the domain. It's not part of the function. Okay, so the derivative, use the quotient rule, and we get minus 4 divided by x minus 1 squared. There are no critical points. X equals 1 is not part of the domain, so it can't be a critical point. That can never be 0. Okay, so this is an example of a function that hasn't got any maxes or mins. What about sine x? Okay, the domain is all numbers, its derivative is cosine of x, and its second derivative is minus sine x. So the critical points, well, when is cos 0? At pi on 2 and 3 pi on 2. And since it's periodic, you can add 2 pi to all those, but just do the ones that are in the period between 0 and 2 pi. Sine of pi on 2 is 1. So the second derivative is minus 1 there. So at x equals pi on 2, it's a maximum. And x equals 3 pi on 2, it's a minimum. Or you can just remember what a sine curve looks like. And you know, the first is a max and the second is a min. Okay, the second module for you is find the critical point of f of x equals x times ln of x. So you're going to have to use the product rule to find the derivative and set that equal to 0. Okay, and I'll just tell you right now, of course, the domain is x has to be positive. So 0 is not in the domain. How do we find global extremes? Well, we find the local extremes as before. That's the first thing you do. And then you have a look. If the domain is a finite closed interval, then all you have to do is compare the values of f at each of the critical points and at the endpoints. And the biggest of them is going to be the global max, and the smallest value is going to be the global min. More generally, if you haven't got a finite closed interval, you're going to have to use the shape of the graph to see whether the desired global max or min exists and identify it. Right? So if it's an open interval, you have to think about, well, what is the behavior of the function as x goes towards that endpoint? Or what happens as x goes to infinity? Okay, so let's have a look at some examples of that. So compare x squared and x cubed. On the interval 0, 1, we have x squared is bigger than x cubed. What is the greatest amount by which x squared can exceed x cubed? So we're looking at the function x squared minus x cubed. The domain is 0, 1. So we can include or exclude the endpoint 0, 1. Doesn't kind of matter, right? Because at 0 and 1, x squared equals x cubed, and so that's not going to be the minimum. So all we have to do is find the critical point. So we take the derivative, we get 2x minus 3x squared. So we factor out the x, we get x times 2 minus 3x. And so that means the critical points are 0 and 2/3. Endpoints are 0, 1. So the max and min have got to be among there. As I said before, f of 0 equals f of 1 equals 0, so that's going to be a min. And f of 2/3 equals 4/9 minus 8/27 equals 4/27. So that is the answer. 4/27 is the greatest amount by which x squared exceeds x cubed, and that happens at x equals 2/3. Okay. Second question. For what positive value of x does f of x equal x plus 9 divided by x attain its minimum value? Okay, so the domain, we're told is a positive x, so x is greater than 0. The derivative is 1 minus 9 divided by x squared. the critical points are x equals plus or minus 3, right? Because 1 minus 9 divided by x squared equals 0 means 1 equals 9 divided by x squared means x squared equals 9. We don't care about minus 3 since that's not in the domain. And as x goes to 0, we see that the function just goes off to infinity, right? Because we've got 9 divided by x. So x equals 3 is where it attains its minimum value. Okay, so that's x equals 3 is where it attains its minimum value, and its minimum value then is 3 plus 9 divided by 3, that's 6. Okay, then for the last example, I'm going to use an Excel file to help us, because then we can sort of graph the function, and then we can use it to answer the question. So it's a complicated function. It's x to the minus 2 plus x on the interval 0, 4. We don't include 0, right, because that's not in domain. So we're going to use the Excel file to estimate the value that makes the function the smallest, and then we're going to use the derivative to find the exact value of x. Okay, so let me find. So here is our Excel file that I've done, and if you go ahead and look at it, if you click on the Y, you see that I've added in x to the minus 2 plus x. I'm going from 0 to 4. So you see I haven't included 0 because it's not in the domain. We want to find the minimum value, and we see that if we look at the chart, we see that we can't really see any detail, and we can see why when we look at the values. These values are so big here. So we see it decreases. So if we stick in, actually start at 0.6, and look at the chart now, there we go. We've got a nice little valley there. And so we can go and we can try and estimate that out. And that looks like around 1.268 when y is around 1.9, 1.8899, okay, around 1.9. Okay, so let's go and then, so we see that there is a minimum, and all we've got to do is take the derivative, set it equal to 0, and solve that, and that will answer the question. We don't have to then classify anything whatsoever. Okay, so let's go ahead and do that. Okay, so what have we got? We got y equals x to the minus 2 plus x. So we're going to take the derivative, and get minus 2 x to the minus 3 plus 1, and we're going to set that equal to 0. So what are we going to get? We're going to get 1 equals 2 divided by x cubed. Right, so because all we did is I put the minus 2x on the other side, and x to the minus 3 just means we're dividing by x cubed. So I cross multiply, I get x cubed equals 2. So x equals the cube root of 2. And that is our answer. And we don't, and if you like, we can go and check a calculator and see that it's around 1.268. Okay, so if I do 2 cube root, it's actually a little bit less, 1.2599. which is less than what we found. Of course, it could be less because we didn't exactly hit the point. Okay, and there's a homework question where you where you use an Excel file to answer a similar kind of question. Okay, that's it for today. Talk to you later.